Hello and welcome to our session for physical sciences. My name is Temba Ngube. Today we will take a look into, the series resistors. So we shall be exploring exactly what happens in terms of, the rate of flow of charge, the potential difference across a typical, series circuit. Also, we'll try and explore, a number of skills in as far as measuring is concerned, which is a very, very critical component of, of science. So we'll try to arrive at certain conclusions and also try to discover a lot of exciting facts with regards to the series circuit. But remember, by now we most certainly aware of a number of aspects. We know what potential difference is all about in terms of the amount of work done or the energy transferred per coulomb of charge. We also know something about current. That current has to do with how much charge passes through a point per unit time. And when we talk of a unit time, we're actually talking about a second. Now let's look at the broader overview and try to locate the series resistors in as far as the broader electricity section is concerned. Right. Okay, so without any waste of time, so we're already familiar with potential difference, which is the voltage, which has to do with work done per coulomb of charge. Okay, we're also aware that batteries are the source of energy because we've indicated the fact that in as far as the circuit is concerned, we are familiar with the fact that the battery is the primary source of chemical potential energy, and then that energy has to do with the EMF, which is a form of potential difference, which has to do with the maximum amount of energy that can be dissipated by a source for every coulomb of charge. Right. So we also familiar with the fact that conductors are actually poor insulators, and insulators are actually poor conductors. So we use different materials to say, okay, charge needs to flow through a material that displays certain physical properties. Okay. So, but our focus for today is specifically on circuits. But which aspects of circuits are we looking at today? We're looking at series circuit with respect to resistance, because this is what it's all about. So this is our focus for today. Right. Now, this is the thought that's going to guide our discussion for today. Okay. Have you ever thought about what happens to the magnitude of current? Okay. I'll underline that. That's the main idea. So when we talk about magnitude of a quantity, we're actually talking about its size, how much current passes through a point per unit time. Okay. When we have more resistors connected in series. Okay. Now, the second thought that's also going to guide our discussion has to do with what happens to the terminal potential difference. That's the voltage. Okay, in a series circuit when more than one resistor are connected in series. So the arrangement in terms of connection is going to be the series type of a circuit. Right. Okay. Now these are the keywords. Now before we speak to the keywords, there are certain very important facts about the definitions that we need to remind ourselves of. The definitions have to do with the terminology, and the terminology is essentially about the language that's going to be used in our discussion. So if you understand the terminology in the context of electric circuits, even understanding the concepts and even trying to discover some of these facts that we want to bring forward today, I think it becomes very important. But remember, our primary source of definitions is the examination guidelines. Different sources would define the same concept in different ways, but in terms of what is acceptable, it's actually what we derive from the examination guideline. So it's an all or nothing kind of an arrangement. What do we mean? It's either you know the definition or you do not. Right. What are some of the keywords that we're going to use once too often than others today? Is a resistor, which is actually a device. So a resistor is a device or an electrical component. Okay, right? While resistance is a quantity, very important distinction between the two. You need to actually be able to differentiate. So a resistor offers resistance. Okay, so the two cannot be used interchangeably to refer to one and the same thing. Okay, yes, these are two related terms, but a resistor is an instrument or a device that offers resistance, which is the quantity. Now, if we talk about equivalent resistance, sometimes we'll talk about effective resistance in a circuit. Take note of that. Okay. Sometimes we talk about total resistance in a circuit. Okay. Now, we also talk about potential dividers. Potential in the sense of voltage, all right? Okay. While we also talk about a series circuit, which has to do with, the amount of charge that passes through a point per unit time, which has to do with the current and how it relates to the potential difference. So these are some of the things that we definitely want to play around and explore and make some of those interesting discoveries. Right. Okay. Now, let's look at resistance as a concept. So resistance, the symbol is capital letter R for now. Okay. We're saying resistance is defined as the opposition to the flow of charges. Okay. Now, flow of charges is something that we all too familiar with. I think at this point in time, would say a resistor offers resistance to current. So the flowing charge is actually the current. So the greater the resistance, the greater the extent of opposition to the flow of current. So the easier the current flows, the lesser the opposition, the lower the resistance. So these are some of the logical deductions that we obviously need to think about. Okay, so that's what, as far as resistance as per the definition in the examination guidelines, right? So different components we're talking about, electrical devices. They provide varying resistance in a circuit. Let's make a practical example. A light bulb is a resistor. In what sense? What do we mean when we say a light bulb is actually a resistor? We are saying that a light bulb as an electrical component, it offers resistance to the flow of charge, or it offers resistance to the current. Okay? Now, the major function of the light bulb is to transform electrical energy to light and most probably some heat. Okay? But if you compare the amount of energy transferred, from one form to the other by a heating element, let's say, your geyser, it could be your heater at home. These two are both electrical appliances, but at the end of the day, the amount of heat energy transformed from electrical by a heating device is greater. Hence, there is greater resistance for a heating component than a lighting component. So you'd say, okay, what in terms of energy saving and consumption at home, you'd also think about the fact that a light bulb consumes less as compared to for example, a kettle. Okay, this is what we mean when we say different components or devices or appliances. They actually offer varying amount of resistance in an electrical circuit. Okay, so an electrical component that has a high magnitude of resistance, that's high resistance, right, will require more energy. Because remember, in a circuit, it's all about the energy transfer or energy transformation. So greater resistance implies more energy conversion, by that particular device. All right, okay? So electrical resistance is measured in ohms. So the ohm, actually, it's actually the SI unit. So we've also looked at R as the symbol, okay? The unit of ohm is omega from the Greek alphabet. So, but remember, ohm is somebody's name. As a result of that, it should always be in uppercase or a capital letter. Okay. Now, how do we define an ohm of electrical resistance? It's when an ohm of electrical resistance allows an ampere. An ampere, it's 1 ampere of current, okay, to pass through a conductor when a potential difference of 1 volt is applied across it. So in other words, we are saying 1 omega, which is 1 ohm, is actually equals to 1 volt per ampere. Okay, if we say per ampere, we are saying there's 1 ampere of current. And when it's 1 ampere of current, what does it mean? It means, a coulomb of charge passes through a point per unit time, right? Okay, now conductors are objects that have low resistance. Now let's look at the physical properties of materials. This is something that we most probably need to remind ourselves as we look into resistance in series. Remember, in terms of physical properties, they are electrical conductors and electrical insulators, which are different from thermal conductors and thermal insulators. In terms of electric current, we talk of electrical conductors and insulators. Now, insulators will be your plastic material, as an example, that does not allow electric charge to pass through them, or current does not pass through them. While electrical conductors, that's your nichrome wire, your copper wire, as you would establish when we use the simulation, we always use the copper wire. Why? Because it's an electrical conductor. So in terms of physical properties, take note of the function of those electrical components in as far as their use in the circuit. Right. And then how do we measure resistance in a simple circuit? We definitely need a cell or a battery, a conductor, a resistor, okay? A resistor can be any device that, it could be a light bulb, okay? It could be even a light bulb, because a light bulb is a resistor. So this is a simple circuit after all, okay? And then we need an ammeter. We know an ammeter is used to measure current passing through a point, the unit time. We also need the switch to complete or break the circuit. We also know that a voltmeter measures potential difference between 2 points in a circuit, right? Now let's look at exactly how one could measure, the resistance of a circuit, which is also an indication of how the flow of charge is affected in a simple circuit. Now let's go to our simulation and actually model that and see what happens, okay? So we've got a simple circuit here with a source or a cell that has got 9 volts EMF, okay? And then the resistance of the resistor there that we have used is actually 10 ohms, okay? The reason why there is a 0 ampere of current in this circuit is because the circuit is broken, okay? How about if we close the switch and complete the circuit, because that's the primary function of the switch. So if we close that, we can see the conventional flow of current which occurs from the positive terminal to the negative terminal. Now, the current reading of 0.9 amperes, what does it tell us? It tells us that there is 0.9 coulombs of charge that pass through any point in this circuit, even through the resistor, for every second. Right. Now we want to establish how our resistance affects the flow of charge, which is the current. Now let's adjust the resistance of this resistor and make it even, let's say double, and see how the rate of flow is affected, which will also be reflected in the current reading. Okay, so if we double that, let's say to 20, right, you can immediately tell that the current is even lesser in magnitude. You can see there is greater opposition to the flow of charge. Even the current reading is almost half of what we had initially when we had a resistance of, okay, if we make it 20, it's actually exactly half the current, which is 0.45 amperes. And what does 0.45 amperes tell us? It tells us that for every second, there's 0.45 coulombs of charge passing through the resistor per second. Right, so that's a simple demonstration of what it means when we talk about the opposition to the flow of electric charge. Right, okay. Now, let's understand now exactly what it means in terms of resistance. A heating appliance or light bulbs, they offer greater resistance than the conducting wire. So the assumption in our simple circuits that we'll set up today is that the conducting wires have got what is called negligible resistance, which implies that we can choose to ignore the resistance of the conducting wires and only focus on the resistance of other components. It could be your light bulb, it could be whatever heating appliance that you connect in your circuit. Okay, so when a component has high resistance, there is more energy transformed when charges move through that particular component. Right, okay. Now, measuring resistance in practice, how do we then measure resistance? We need to ensure that we measure the potential difference in current through that resistor. So if, for argument's sake, we had, if we can quickly go back to that simulation, okay, now we are able to measure the potential difference across the resistor. In this case, there is our potential difference. Our potential difference is 9 volts. And then how much current actually passes through that that resistor. It's 0.45. Now, we are able to determine the resistance of this component by using, if we can quickly go back to our our slides, would understand that for us to calculate resistance, we need the magnitude of voltage, which is the potential difference across the resistor, as well as the current passing through it. By so doing, we are able to determine how many ohms of resistance a particular component offers in a circuit. And remember, 1 ohm, right? We're saying 1 ohm, okay, which is the SI unit of, of resistance, is equals to 1 volt per ampere. So this is where it comes from this mathematical equation. Right, so that's as far as determining resistance. So when we come back, we'll try and explore how current varies or potential difference, what happens to potential difference in a series circuit where we have got multiple resistors that are connected in series. Let's take a short break for now. Welcome back to our second segment. We're still exploring resistors in series in a series circuit. Safe to say that we also now are familiar with how we exactly measure, the resistance of a resistor in a simple circuit. We need to have the voltage across that resistor, as well as having an awareness in terms of how much current passes through that resistor, which is the amount of charge that passes through that component per unit time, right? So now to measure the total resistance, this total resistance will be our effective resistance in the circuit, okay? Then we need to have an indication of the terminal potential difference. This is the voltage across the battery when there is current in the circuit. And we also need to know how much current passes through the battery. And then this is the total current, right? That's the total current in the circuit, because all the current will pass through the battery. So this is total resistance. We would abbreviate it as R subscript T. Okay, so if we have the terminal potential difference, which is the total voltage again, we have also the total current, we are able to determine how much total resistance we have in a given circuit. Right, now let's use a simulation to kind of look into how exactly we measure terminal potential difference, as well as, the total current in a simple circuit. Okay, so if we go to our simulation, okay, we have something of this sort. Okay, there is no current in the circuit, because we are saying that in this circuit, the circuit is broken or the switch is open. But the moment we close the switch, there is current that is registered in the circuit of 0.9 amperes. Okay, so if we are to determine the magnitude of terminal potential difference, we would actually go to the battery and actually measure the potential difference across the battery. In this case, it's 9 volts. Now, the resistance in the circuit is a result of us understanding what's the terminal potential difference, as well as what's the total current passing through the battery. So if we can also use the value of potential difference across the resistor, it will give us the same thing, because this is the only resistor in the circuit, so it gives us the total resistance. So the voltage across the resistor is actually equals to the voltage across the source. Okay, so that's our value of terminal potential difference, while the current is not 0.9. But this is only possible if the circuit is complete. But if we decide to break the circuit, there is a potential difference of 9 volts, which is actually the EMF, which is also equal to the terminal potential difference. What does that tell us? It tells us that this battery does not offer any resistance in the circuit. So if we got the current reading and the terminal potential difference reading, we are able to determine the total resistance in this circuit, right? Okay, going back to our slide. Now, here's a scenario. If the total voltage in the circuit was 9 volts, okay, and then the total current that was registered is also 0.9 amperes, then obviously the 10 ohms comes from R is equals to total voltage, okay, divided by total current. So this is total resistance, okay. That's how we get the 10. So it's 9 over 0.9, which gives us the 10 ohms, right? Okay. Now, to measure the resistance, this is what we are saying. You must measure the potential difference across the component. Now, in this case, when we talk about the component, we actually talking about the resistor itself. It could be a light bulb or whatever the case may be. So if we measured the total resistance by measuring the terminal potential difference, this gives us an indication of the total resistance in the circuit, provided we know how much current passes through the battery. But now, if we are to measure or determine the resistance of a component, the potential difference must be measured across the resistor itself. And we must know how much current passes through that resistor. Then we can get the resistance of that particular component or resistor, okay? Now, so the current passing through the resistor is also very important, because now, let's say we talk about resistor 1 for argument's sake. So resistance of resistor 1 is equals to voltage across resistor 1 divided by the current that passes through resistor 1. So take note, we're still using the very same mathematical equation to determine the resistance, right? Okay. Now, we can do that using a simulation and get a sense of what exactly we are talking about. Okay. Now, if we are to measure the voltage across the resistor, we'll obviously take the terminals across the resistor. It gives us 9 volts, and then there is a current of 0.9 amperes passing through the very same resistor. So we can, if we say this resistor is R1, then we can determine the value of R1 using the voltage across R1 and the current passing through R1, right? Simple, straightforward. There's nothing, rocket science about that. Okay, so this is what basically we have verified. Okay. Right, now we want to measure resistance, okay? This is what we are saying. There's only one, if there's only one resistor in a circuit, as we have seen in the previous example, the resistance of the resistor is equal to the total resistance of the circuit. So in the case of R1, being the only resistor in the circuit, so if we go back to the table of results, so the total resistance is a result of R1 being the only resistor in the circuit, okay? So in other words, resistance of R1 equals to R total, if and only if R1 is the only resistor in the circuit. So we're simply trying to say, as long as there is a single resistor, that resistor is what accounts for the total resistance in the entire circuit, right? Okay? Now, we are clear with that. And then we are saying that the other assumption that we are working on is that the ammeter, which is always connected in series, and the conducting wires, okay, have negligible resistance, okay? Let's try and unpack that term. If we assume that the conducting wires and the ammeters that are connected in series actually have got negligible resistance, it says to us that the resistance in the total circuit, is offered by other component except for the conducting wires and the ammeters. So all the current will pass through the ammeter. So the ammeter in itself, as well as the conductor, they do not provide any opposition to the flow of charge. That's the main thing about it when we say it's negligible. So the term negligible resistance will be used, in many of the circuits that we shall try and explore as we go along. Right? Okay? And then here's a thinking question about measuring resistance. What happens to the total resistance? Okay, we're talking about R total. Take note of that, of the circuit when more resistors are connected in series. This is a thinking question, okay? Now, here's a scenario. Instead of having just one resistor, we'll add another resistor. Whether it's identical or not, it doesn't matter. Now, let's go to the simulation and try to explore that as well. Okay, so that's our circuit. Okay, let's add another resistor to this circuit and see exactly what happens when we add more resistors in series. Okay, right. Okay, just to create more space for that. Okay, so that's our one resistor. Okay, we'll add another one. Okay, of same resistance, just to make life much easier for us. Okay, right. So there are two resistors there that have been added. So we've added one. There are two identical resistors. R1 is 10 ohms. R2 is another 10 ohms. Okay, now the question that we asked, what happens to the total resistance when we increase the number of resistors in series? Okay, but remember, what is resistance? Resistance is the opposition to the flow. Okay, so if we are to demonstrate that, let's use the conventional current just to show what is happening. The amount of charge that passes through our ammeter has actually been halved. It was 0.9, now it's 0.45, which is half the original. Okay, it means that if we add more resistors in series, what does that tell us? The opposition to the flow of charge increases. That's effectively the resistance of the circuit. So if the first one is R1 and the second one is R2, the total resistance has increased. That's why, which explains to us that the value of current has also decreased. Okay, now if we realize that there is a decrease, so if resistor 1, the voltage across resistor 1 is something that we also need to measure. Okay, but the current that passes through both of them, it's something else. If we are to measure the voltage, okay, so the voltage in this case, there is a voltage. Okay, the voltage is 9 volts. That's the terminal potential difference across the source. Okay, now in this case, this one is going to be 4.5. What if, for argument's sake, we change the resistance of this one to make it, say, for argument's sake, half that one, and see what happens? Okay, if we make it half, it means it's going to be 5 ohms, right? So if it's 5 ohms, okay, this is the voltage across R1. So R1 is 10 ohms, R2 is 5 ohms. Now, the total current is decreased from 0.9 to 0.6 amperes. But I just want you to check something very important. Our terminal potential difference, which is the total voltage, is 9. Okay, look at the voltage across R1, okay, which is 6 volts, and then voltage across R2, it's 3 volts. Okay, if you say 6 plus 3, it should give you that 9. Okay, it should give you the 9, right? So if we go back, okay, resistor 1, the total resistance is 15 ohms. Okay, the resistance for R1 is 10 ohms, right? Resistance for R2 is 5 ohms. This is what we realized. Okay, that's the total current. Voltage across R1 is 6 volts. Okay, across R2 we measured it to be 3. Now the total current, we can determine the current that passes through each one of those. Okay, as you can see, there is a single path for current to flow. It means the same amount of current passes through R1, through R2, as well as through the battery, which is the source. So there's a constant amount of current passing through. So we still have a 0.6 there and 0.6. Okay, now if you realize that if we add more resistors in series, the total resistance has increased, which has decreased also the total current in the circuit. That's the main idea that we wanted to actually explore, right? Okay, now, okay, what happens to the resistance of resistor 1 when connected in series with a second different resistor? We realize that the resistance doesn't change, okay, of R1, because if we go back to our simulation, if we calculate the resistance of R1, we've got 6 volts versus the 0.6 amperes. It will still give us the same, 10 ohms, okay? But also, if we calculate, we measure the voltage across R2, which is 3 volts, divided by the total current. This will give us 5 ohms, okay? So, which is exactly the value. But if we also measure across R1, it gives us an indication that also it's 6 volt. But there's something very interesting about the total voltage in this circuit, which is something that we want to arrive at. Okay, so this is a big question. What happens to the resistance of resistors R1 when connected in series with a second resistor? Okay, right. So we have measured the 6 volts and confirmed that, which is fine, right? Now, for R2, we also realized that this is 3, okay, which gives us the total of 9. The same amount of current passes through each one of them, including the battery, okay? And then this was half the resistance of R1, okay? Okay, that's the main idea, right? Okay, so we have confirmed these results. Also, measuring is a very, very important skill in the scientific process, and also how then we use that data to analyze, okay? We need to arrive to some sort of a logical conclusion. Now, in terms of measuring resistance, what conclusion can you make about the relationship between the total resistance in a circuit and the resistance of the 2 resistors? It was straightforward. We had the 15. So this 15, which is the R total, actually comes from the sum of R1 and R2. So we can immediately project from this that the more resistors we add in series, the greater the effective resistance of the circuit, right? Okay, so this is actually the main point about how we determine resistance in a series circuit. So the more resistors connected in series, the greater the equivalent resistance. So if we talk about equivalent resistance, we're talking about total resistance. Sometimes we would refer to it as the effective resistance of the circuit, right? So that's the main idea. So in as far as measuring, we need to determine the amount of voltage across a component, okay, so that we are able to also know how much current passes through it, and then we can use the mathematical equation R is equals to V over I. But the main idea about the simulation that we just explored is that as long as we continue to add multiple resistors in series, the effective resistance of the circuit will increase. Let's take a short break for now. Welcome back to our third and final segment. We're still exploring resistors in series. Now we want to take a look at how adding more resistors in series actually affects the magnitude of current in a series circuit. Okay, so what we have done now, we are able to understand that in the context of circuits, right? We've got a series connection, which is our focus, and we understand that in a series circuit, the more resistors you add in series, the greater the effective resistance of that particular circuit. Now we want to take a look at how that exactly affects the magnitude of current, right? Okay, so in a series circuit, what is it that we notice about the current in the circuit, okay? And the potential difference across it when we add more resistors in series, okay? Because that's the context. So what we've changed is actually the number of resistors in series. So we have got 2 resistors. We started with one of magnitude 10 ohms, which is R1, right? So, and we managed to measure the resistance of that particular resistor, which is actually equal to the total resistance in the circuit, by measuring the voltage across the R1, and then knowing how much current, then we can use the mathematical equation. Resistance of R1 is equals to voltage across R1 divided by the current that passes through R1. Now we want to add a second resistor. However, the second resistor is actually half the resistance of R1. So R2 is actually half of R1, and R1 is double R2. Make sure that you understand that mathematical relationship. So we're saying that our first resistor is a 10 ohm resistor, okay? And then the one that we're gonna add in series is actually 5 ohms, okay? Now we are saying that R1 is equals to twice R2, okay? So make sure that you understand this, but effectively, adding the two resistors, we got the total resistance of R1 plus R2, which is actually equals to 10 plus 5, which gives us the total of 15 ohms, right? So that's our R total. Now we want to understand that if we add another resistor, how is that going to have an impact on the size of current through the battery, through each one of them? But remember, in a series circuit, there's only one path for current to move in the circuit, right? Okay, so this is what we realized, is that the total resistance, if we used, let's say for argument's sake, a resistor of 6 and 3 ohms, it will give us a total of 9. Okay, the voltage was actually 9 volts because the other resistor one across it was 6 ohms. Okay, 6 volts rather, because that's the voltage, right? So, and then the total that I'm trying to refer to is actually the 15 ohms that we managed to get from the sum of these two. And then we want to verify what happens to the current in a series circuit, right? Okay, let's go to the simulation very quickly. So we've got two resistors here. The first one is 10 ohms, that's our R1. The second one is our R2, which is half R1, which is 5 ohms. The voltage across the source, whether the switch is open or closed, we realize that it's 9, okay? Now, there is no current in the circuit. Why? Because the circuit is broken, okay? But if we decide to close the switch, there is current in the circuit, okay? Now, if we start by maybe verifying the values of voltage across each one of those components. So our terminal potential difference is the voltage across the source, right? That's the voltage across the source when there is current in the circuit. That gives us 9 volts, right? So this is our V total, or terminal potential difference, while V across resistor 1 is equals to 6 volts, okay? We are verifying that. And then voltage across R2, is equals to 3 volts. So the sum of 3 and 6 volts gave us the total of 9 volts, okay? But how much current passes through R1? You'll realize that before R1, there is 0.6 amperes of current, okay? After R2, there is 0.6. Even if we put another ammeter, we would also understand that the same amount of current, even through the source, the same amount of current will pass through it, okay? So this drives us to the, the conclusion that in a series circuit, solely because there is only one path for charge to flow, then the same amount of charge passes through every point per unit time, which is equals to 1 second, right? Okay, if we go back to we can verify that we had 0.6 amperes through the battery. So this is actually, the total one is through the battery, okay? So this is the current through the battery, okay? We need to be very careful about that, because this is through the battery. Now this is through R1, okay? This is through R2, right? So what do we notice exactly? Now let's take a look at how we are going to examine the results that we just collected. So the question was, in a series circuit, what do you notice about the current in the circuit? Now we are saying that the total current, I total, take note of the notation, is the current through the battery, okay? This is the total current in the circuit, in other words, okay? The current through the source, which is the battery, okay? And then when we talk in terms of notation about I1, sometimes it will say the reading on A1. A1 becomes the ammeter that registers the current passing through R1. So this is actually the current through R1 for argument's sake. And then when we talk about I2, it's actually the current that passes through resistor 2, and so on, okay? Now, we realize that the magnitude of current, if we can quickly go back to that, the magnitude of current that passes through each one of them is actually the same amount, okay? So through the battery, we would have 0.6 amperes. Through R1 and R2, it's also 0.6 amperes. What is the thinking behind that? There is only one path that current uses actually in the circuit, right? So if we agree that, okay, that is the notation. So in conclusion, if you're saying I total is equals to current through resistor 1 is equals to current through resistor 2. So for n resistors connected in series, the total current is equal to the current that goes through each of those resistors. Hence we're saying that in a series circuit, right? Okay, this is the main conclusion, okay? In a series circuit, current remains constant. So we use this data that we collected to actually arrive at this conclusion, okay? Current remains constant. So if a quantity remains constant, it means it does not change, right? Okay? Now, the other one now, we want to predict what will happen to the current in the circuit when you add even more resistors, okay? So we started with you know, a single resistor. So if we added more resistors, what effect did that have on the total current in the circuit, okay? So if we, just to go back a little bit to make that comparison, okay? Suppose we take out resistor R2, okay? If we take out resistor R2, right? And then we complete that circuit, okay? You realize that with R1, which is 10 ohms only, the total current in the circuit is 0.9 amperes. Okay, suppose let's break that circuit and then add the other resistor so that we can actually get a sense of what happens in as far as the total current in the circuit. Take note, with only R1 of resistance 10 ohms, the total current was 0.9. What if we add R2, which is 5 ohms, which is half R1, okay? We want to just make that conclusion, that observation. So to change that to 5 ohms, okay? If we change it to 5 ohms, it will give us, okay? That's the circuit. So R1 is 10 ohms, R2 is 5 ohms. Let's close the switch, okay? Now the current has dropped to 0.6 amperes. Okay, why? Because the total resistance in the circuit has increased. So if we increase the total resistance in the circuit, effectively we are increasing the opposition of flow of charge, which means there is greater resistance. Hence, there is lower current flow in the circuit. Okay, so that's a very important observation to take note of. Okay, so when more resistors are connected in series, what are we saying? R total in the circuit, which is the total resistance, will increase, okay, while the total current will decrease, okay? So current will decrease while the resistance increases. So where does this come from? Okay, remember, we did not change the terminal potential difference. Is still 9 volts, okay? So that 9 volts is actually split between R1 of 10 ohms and R2, which is half the resistance of 5 ohms, okay? So increasing the resistance, actually in not so many ways, what are we saying? It actually increases the opposition to the flow of charge. And the flow of charge is actually the current. So at a higher resistance, there is a correspondingly lower current, right? That's the main issue, again, that we need to take note of. Okay, so in a series circuit, what do you notice about potential difference across the resistors? So if we quickly go to our simulation, let's measure the potential difference across the resistors, okay? So our terminal potential difference, to verify it once again, it's 9 volts, okay? Voltage across R1, it's 6 volts, okay? Voltage across R2, it's 3 volts, okay? The 9 is split between the R1 and R2. And if you do the total of 3 plus 6, it gives you the terminal potential difference. That's the main thing there, okay? Right, so we realized that the 6 plus 3, okay, gave us the total of 9. So this is V total, okay? So this is V across R1, okay? This is V across R2, right? So if you add the 3 plus 6, and 6 will actually get that 9, okay? So we've done that, okay? So in a series circuit, what is it that you notice about the potential difference of resistors? In conclusion, we can say that the voltage or the potential difference across the battery is divided in proportion to the resistance of the resistors. You'd realize that V across the 10 ohm, okay, is equals to we got the 6 volts, and then V across the 5 ohm resistor is equals to 3 volts. Okay, so if you say V across R1 plus V across R2, you will actually get your V total, which is your terminal potential difference, right? Okay, so the resistance is the opposition to flow. This is what we know, and an ohm is a volt per ampere. This comes from R is equals to V over I, right? Okay, and then in closing, we understand now what happens when you increase the total resistance of a circuit by adding more resistors in series, okay? Because that's the scenario that we had, okay? If you increase the resistance, the total current actually decreases while the total resistance in the circuit increases. So in as far as resistors that are connected in series, two very important points that we take home is that increasing the number of resistors in series increases the total resistance. At the same time, it lowers the current. Hence, we would say a series circuit is actually a potential divider while current remains constant. That's all we had for today. For now, let's take time to reflect on some of the discussions that we have. Otherwise, that's the gist of a series circuit. For myself, for now, it's cheers and bye-bye.